I'll be talking about structure property approach to the fusion in bilayer organic solar cells.
The title has changed slightly. Okay. The title of my talk today is the evolution of morphology in solution processed bilayer organic solar cells. So as you are well aware, state-of-the-art technology is the bulk entry junction solar cell. So the question you might ask is why make bilayer OPV cells? Because they generally have lower efficiency due to the reduced interfacial surface area, and the layers are generally thicker than the exciton diffusion layer. However, they are simpler to fabricate. You don't have to worry about the nanoscale morphology control that you encounter in BHJs, and you're able to optimize each layer. And this also represents a good platform to test new acceptor and new donor materials. Now recently, the group from UCLA demonstrated an all-solution processed bilayer OPV cell. If it's true, this is quite exciting because this provides a pathway for inexpensive, large volume fabrication. The key technique here is to use a pair of orthogonal solvents, in this case dichlorobenzene and dichloromethane, to spin coat sequential layers of P3HT and PCBM. In their paper, they reported performance that was comparable to solution processed BHJ cells. It's a bit surprising as the donor acceptor layers in their device was much significantly thicker than the exciton diffusion length. And they claim that the exciton diffusion length was much bigger than the generally accepted value of 10 nanometers. They attributed the improvement from being able to optimize the processing condition for each layer separately, in particular increasing the PCBM crystallinity, therefore thereby improving the mobility of the electron through the PCBM. Okay, this is a quick slide showing you how to make these devices, and this is the fabrication process that we have developed at Code, based on the previous paper. So basically you spin coat the P3HT, you let the P3HT dry, then you spin coat the PCBM layer on top, okay, and I'll refer to this structure as the as-cast. Then you anneal it, okay, and this is what I'll refer to as the annealed. And after that, load it in the evaporator and deposit the top electrode. So, fairly straightforward. On our substrate, or device set, we can make 6 devices. And compared to our best BHJ, and also the bilayer that was reported by the UCLA group, we've been able to improve the device performance. So this shows the JV characteristics of our best bilayer and the best BHJ, okay? And you can see that the fill factor for the bilayer is better than for the BHJ, and the VOC is slightly better. And this is reflected in the device performance parameters shown here. For the BHJ, it's 3.7%, and for the bilayer, 3.8%. It also showed you that this wasn't just a fluke, we can do this repeatedly. So that's another device set. Okay, also you know that for BHJs, they have to be annealed to achieve high efficiencies. This is due to the nanoscale morphology and to improve the crystallinity in your donor and acceptor. To investigate the effects of annealing, we prepared 2 device sets. One on which we annealed after the PCBM spin coating, which is what we do as a normal process. And on the second device set, we just had an as-cast PCBM layer and deposited the electrode on top of that. Now you can see here that the annealing has a significant impact on the device performance. This is for just the as-cast, and the blue is for the best annealed device. And from the performance parameters, you can see that the efficiency drops by 1/3 if you just basically use an as-cast device. So this shows that the bilayer device must also be annealed. But the question here is, is it the same phenomena, and also, what is the device morphology? So first, we turn to optical characterization to get an idea of what's happening in the film. From the absorption spectra, shown here, okay, this is the normalized absorptions. From the effect of annealing has a minimal effect on the highly ordered P3H2 layer. So that's what the absorption spectra is telling us. From the PL, we looked at exciton quenching, okay, and we also excited, in this case, we excited through the substrate. In the ASCAR structure, which is the green trace here, you can see that the PCVM quenches the PL by up to 90%. And in the anneal, you get a slight increase in the PL, and this is due to the decreased exciton quenching. Now, I'd like to point out that also in the paper by the UCLA group, they observed the same effect. So the orange dots here is for the ASCAR, and the green is for the anneal bilayer structure. We think this is due to PCVM clustering. In their paper, the UCLA group attributed this to the sharp polymer fullerene interface forming. Okay, what about the surface? Because the film electrode interface is very important for device performance. We turn to X-ray photon electron spectroscopy, XPS, to probe the composition and the morphology of the top 5 nanometer of the device. This is a survey scan from the XPS for the ASCAR and the anneal structure. And the surprising thing here is that you get the peaks from the sulfur, and the only material that has sulfur is the P3H2. So even in the ASCARs, you can see that there is a small amount of P3H2 on the top surface. And once you anneal it, as you can see in the blue trace, there's a significant decrease in the PCVM concentration because the sulfur peak rises quite considerably. Now, if you look closely at the carbon 1s peak, okay, what you see for the ASCAR sample is contributions from the carbon-oxygen functional group from the PCVM. They're in the ratio of 1 to 1, as you'd expect. And once you anneal, you see a significant decrease in the contribution from those functional groups, and at the same time, a rise in the contribution from the carbon-sulfur bond over here. So where is the PCVM going? Well, we think it's going down into the P3H2 layer. Also, at the same time, one of the nice techniques about XPS is that you can do angle-dependent measurements. So we take the spectra at 0 degrees, which is a sample sitting flat, and at 70 degrees with the sample tilted at a large angle. And at 70 degrees, you can improve the surface sensitivity. And now here, what you see is that the relative intensities of the contribution from the carbon and the sulfur are the same at both angles. So the green is for the ASCAR, blue is for the anneal, and red is for the measurements at 70 degrees. So you can see that the peak intensities are the same. So what this is telling us is that the top layer is homogeneous. It's mixed, and there is no distinct PCVM layer at the top surface. Now, what about the vertical morphology? Because the XPS only tells you about the top 5 nanometers. To get an idea of that, we turn to Neutron Reflectometry. But I'd just like to point out that there's been some work done on using Neutron Reflectometry on the P3H2 PCVM system. There's been a recent paper in Advanced Materials from the Sheffield group, and also NIST has also been looking into this as well, and that was reported at the MRS spring meeting. Now, luckily for us, P3H2 and PCVM have a significant difference in the neutron scattering length density. For P3H2, it's been measured to be 0.8, while for PCVM, it's between 4.5 and 4.8. So it's quite good. These measurements were performed at Anstone, down in Sydney. That's where the only nuclear reactor is in Australia. And this was done on 2 in-silicon wafers, and we prepared the following 2 films. The sample 1 was just a film of neat P3H2, so that we could measure the scattering length density for the P3H2. And sample 2 was the bilayer structure. So initially, this was the ASCAR structure, okay? We measured the neutron reflectometry profile, and after that, put on the hot plate, anneal it, as we do for the device fabrication, and then measure the profile again. Okay, the top graph shows the obtained profile. So basically what you're looking at is the intensity of the reflected neutrons as a function of the incident angle. And you see these peaks because of the constructive and destructive interference of the reflected neutrons. So the red is the P3HT film, green is annealed, and blue is as-cast. From the profile, if you do some modelling, like after it's performed, you can extract the morphology, and this is shown here. So the red trace is of the neat P3HT film. You can see that it's of the same SLD, so it's a single, it's a uniform film. Now the blue trace shows the as-cast sample. You can see it shows a bilayer-like structure. The top layer, which is 22 nanometers, is PCBM rich, because the SLD is quite high, while the bottom layer, 60 nanometers thick, has a much lower SLD. But the important thing here is that the lower SLD, the lower layer SLD, is actually higher than the neat P3HT. So it's not pure P3HT on the bottom. So what's happening here is that the DCM is causing the P3HT swell and allows the PCM to diffuse into the lower layer. And we saw from the PL quenching that even in the as-cast, you get quite a significant quenching. And also at the same time, this doesn't disrupt the ordered domains of the, ordered P3HT domains, as we saw from the absorption spectra. So this is fairly consistent. Now the green trace shows what happens after the annealing step. And you can see that the annealing causes a change in the morphology. The PCBM diffuses and becomes more evenly distributed throughout the film. So this cartoon here shows what's really happening. Basically you have a PCBM-rich layer at the interfaces and a mixed layer of P3HT and PCBM. So in a sense, we've achieved blending between the P3HT and PCBM unintentionally. I mean, that wasn't the reason why we did the annealing, okay? So in conclusion, the combined optical, neutron and X-ray analysis clearly show that the P3HT PCBM intermixes from the moment when you spin coat. So, just to summarise, when you spin coat, you end up with a PCBM rich layer on the top and a P3HT rich layer on the bottom. And the subsequent annealing process gives you a BHJ-like layer with PCBM rich layer at the interfaces, but a mixed layer, but which still maintains the ordered domains of the P3HT. Also, I showed to you today that the morphology clearly affects the device performance. We get an improvement, a significant improvement in the device performance due to the PCBM diffusion into the active layer due to the annealing. So this is slightly different to what the reason why you do the annealing in the BHJ, that is to improve the crystallinity, okay? As I demonstrated before, you already have good crystallinity in your as-cast structure of the P3HT. And lastly, this is a fairly elegant way to make OPV cells. You can just basically put one layer at a time, have it mixed. You don't have to worry about mixing donor and acceptor together in the right ratio and all that. So it's a fairly neat way of doing things. Thank you.
Any questions for Kwan? John?
So the neutron reflectivity was done on a silicon substrate.
Yep.
Is that correct?
Yep.
So could that not introduce deviations in the vertical segregation because of surface energy issues?
I mean, that's something we've considered as well, and we've checked through microscopy and all that to make sure that the spin-coated films looked identical. So we're fairly confident that the film that you get on the silicon wafer or on the glass substrate are comparable.
But what about on PDOT, for instance?
What do you mean?
So would you get the same end result if you had PDOT as opposed to silicon?
Yeah, that's a good question. I mean, obviously, with the neutron reflectometry, you can't put PDOT on it because that will, affect the measurement. But once again, I think just from the just look at the microscopy, looks fairly identical. So, I mean, if there was phase segregation or if you had anything changing, then yeah, we'd be a bit worried, but we wouldn't see anything like that. Yeah.
Just a remark, One way of determining an excitome diffusion rate is to put a polymer on, for example, C60. That's what people did, and then you do the squinting experience. And but from that you get a too high value. And it appears that even C60 itself does go into the polymer. So the only way to get rid of that is that we did that with Paul Blom. We developed a cross-linkable polymer. And you take that and you cross-link it and then you spin coat it. That's the only way that I'm pretty sure of that you really get a sharp interface without distribution. Because that cross-link film you can wash with ODCV for a night and it doesn't change. So that's the only way to be sure that you don't have diffusion.
Did you say cross-link fluorine or cross-link polymer?
No, cross-link polymer. Yeah.
We get some.
Yeah, the problem is that it's not really convenient to make. But no, it's a lot of work. That's all.
Gary first.
When you say that the two samples aren't soluble in each other's solvents, did you test that? And the reason I ask the question is that because polydiethylene has quite a wide distribution in molecular weights, and the low molecular weights almost certainly do dissolve into the dichlor. Was it dichloromethane?
Dichloromethane, yeah.
So I think a nice experiment to try to take the polydiethylene, dissolve it into your dichlorobenzene, and then dump it into dichloromethane, and then use the precipitate to redissolve that. And then that way that you should in some way prevent the polydiethylene coming up into the CDM.
So, I mean, in the paper from the UCLA group, they did that experiment. They washed their P3HC in DCM and then used that P3HC to spin correct the P3HC film. And they demonstrated that, washing or not washing made very little difference in terms of device performance. So, but obviously, I've dropped DCM onto the P3HC, layer and doesn't wash away. It stays as it is. So I'm fairly, happy that it doesn't dissolve away in the DCM P3HC layer.
Question.
I have actually two questions. First, one for you, Keith. When you cross-link the fullerene, does it not affect the electron accepting properties?
No. we designed it in such a way that you do not cross-link the fullerene, but you cross-link the side chain.
The side chain.
Yeah. So the fullerene remains a mono-substituted mono atom. Right?
Okay. Then my second question is for Kwan. I mean, you have PCBM rich on both sides of the mixed layer, so is there not an issue for whole drift?
Oh yeah, I mean, it is an issue, but it's something we haven't been able to control. Obviously, it would require more fine-tuning to try and prevent that. I mean, interestingly enough, I saw a slide from this group, and they see the same effect as well in their BHJ. The PCBM likes to pull up at the two interfaces, and obviously, I've been told that that's that's been submitted to a journal. I don't know which journal, but we'll see that soon. And it was from a summer school slide actually, and they showed the same thing, that the PCBM just pulls up at the interfaces.
I'm not questioning your picture there. I'm just asking. I mean, it cannot be good for all transport.
Yeah. Yeah, I mean, that's what we end up with. So.
Yeah. When you end up with a 3.8% cell with a huge fill factor. Yeah. No inflection.
In spite of the very
In spite.
what should be a problematic whole transport.
Still works.